Dominik Schreier, I'm from ITK and I'm talking about Tailormade embedded software solutions, and today it's about model-based systems, and we'll show you from the idea to the verification and validation what you can do on model-based design. First of all, you will get a small overview of ITK and our motorsports department, and then we will start with the model-based software development, so how to make race cars intelligent and what you can do for verification and clarification. Sorry. Okay. So, yes, ITK was founded in 1994 in a cellar with, they started from zero and went up to 1,300 employees worldwide. We have 10 locations in Germany and 5 locations worldwide, but what is not complete true, because it's in Austria, not only in Vienna, we have also in Graz, Linz departments. So in Austria we're using the Bosch departments and are also located there. And since 2017 we are 100% daughter of Bosch. And yeah, this is why we use their office departments. At ITK we have system engineers, guys who are taking care of cybersecurity, control, system design, image and signal processing, and cognitive solution. And this is all spread over different fields. So we have guys working for industry, automotive, rail, commercial vehicles, highway vehicles, healthcare and motorsports. And the good thing is that we can use all these guys from all departments in our projects. So for example, in motorsport we have also guys from, why is it changing? Sorry. Sorry. No, it's okay. In motorsports we are helping, or we have projects from design through development up to the race. So we start with requirements analysis, we help to develop concepts for drivetrain, EE architecture, and also system solutions for simulation. And in the development process we are helping with, I don't know why this is changing all the time. Okay, I don't know. We have guys who are supporting in the testing area with hill tests, vehicle tests, even simulator tests at DILs, and we have with the help of the implementation of battery management systems, drivetrain, or energy recuperation. So we have in the development a lot of guys working, and we also support our customers in simulations for the race. So driver training, race strategy optimization, lap time simulation, and even on the track we have guys who can help there and assist. So this is also possible, and yeah, these are the fields we are working in. And yeah, our business unit for Motorsport was founded 2017. We have around about 25 engineers in our Motorsport projects, and yeah, in different classes. And these guys are not only from the motorsports department, so we have also guys who are working normally in other projects. Yeah, they help us to to develop what the customer needs. So, in which racing classes we were in Rally Dakar, Formula 1 projects, Formula E projects, DTM, IMSA Series, and Le Mans. And even there we have different customers. This is strictly divided. So if somebody is working with a customer from Munich, he has normally no contact with guys from ITK Motorsports who are working with a customer from Stuttgart. So there's a border, and we don't. There's no information coming from one side to the other, and normally you are also not changing the project. So like yesterday, I worked for one department, for a customer in Munich, and then the next day for the other one in the same project. So we're taking care that this is strictly divided. Yeah, I don't know, what is it? Is it mouse? Model-based software development to make the race cars intelligent. It started with just wires and perhaps one button to turn on the light, up to cars where the light goes automatically, or navigation, internet, ECU networks, where every unit has its own ECU. For example, in normal series production cars, you have for the gears, for the climate, for everything an own ECU, this goes on, and the share of software components is growing and growing, and this also happens in motorsports. There were times you just push the button and the light goes on, and now the driver can decide for himself what he wants. For example, if he presses the flashlight, what sequence should be shown, or different for example, also different wiper settings, which are a lot different from normal settings, because there you can change so how fast is the angle going and how far, and so on. So everything is intelligent, and for everything you can make special functions, and this is done mostly in model-based software design. You have the graphical modeling, where you see, I don't know what's going on. Where you have your functions, interfaces, also have the documentation and the architecture. You have automatic code generation. You have a complete tool chain behind it, and you can use it from documentation up to development, to simulation, real-time debugging, automatic checks, and these are the advantages. And this is all possible in MATLAB, where you can do everything. For the classical embedded programming, you normally have your requirements from text to some UMLs, and then you take your hand coding and write your specific code, which is then compiled to your machine code. The advantage is that it's really hardware orientated, and you can use the memory access and take care of this, and you can really develop for your hardware, and can program optimizations and functions for your hardware. This is the big advantage. The disadvantage is, for example, the lack of clarity in the systems. So if you have big complex systems, you have then like thousands or 10,000 code lines, and you don't have an overview of what is happening where exactly, and it's difficult to scale it and to get to know the system. And with the model-based approach, you can use it. You have your requirements, functions, and your documentation in one piece. So you can start from the scratch and use your requirements, and if you do it correctly, it's very clear and consistent, and the code generation is done automatically, and then after that it's compiled for your ECU. What's disadvantages? You cannot change, or it's difficult to change the generated code. And it could be difficult if you have complex requirements, and these are the disadvantages. The normal development process, you use the V model, so from the idea to verification and validation, and we are showing this on a small example. You can see this also on our pop-up stand in the team launch, where we show this and where you can go and see this in detail. So we have a function ECU and an environment model ECU, and these are there you can implement your functions which you develop on MATLAB, and you have a CAN communication, you have your analog IOs, and you can use it like a small hill system. So this is you can simulate and test the electric drivetrain. You have like I said before, and the big advantage for you, if you use something like this, you have a small budget hill system with Arduinos, and you can develop from there and take this every season. And with the advantage of model-based design, it's fast understandable for nearly everybody, and it's a clear system. So we have the use cases and requirements demanded by the customer. There are functional and non-functional requirements. Functional requirements in case of what are my user interactions, inputs, outputs, and use. The goal is from the analysis to collect and structure and validate the given requirements. Typical problems there with customers or even within team members is often the communication, because they often don't know what they really want, or you don't understand each other because you're speaking in different languages, in quotes. So because not everybody is on the, that deep in every topic, so you have to coordinate this and to talk and clarify it. You have to check that you have the completeness of everything what you need. Often you have changing requirements because you then see, we need something completely different, or we need extra functions, and this could be difficult. So in our example, we have the general requirements. We had Arduino boards. We wanted to use model-based software development for an electric vehicle. For example, a function which no recuperation for SOC is greater than 98%, and torque cutoff for battery errors, so I talked before. So you can use the functional and technical architecture. On the functional architecture, you start and say, you concentrate on your functions. So what functions do we need? We need torque target driver functions. We need the torque limitation and application. And we have our inputs and outputs. And the technical architecture is then how can we achieve this? So what do we need? We have our analog inputs with the throttle and brake pedal. There we calculate the driver torque. On the other side we have our inputs from SOC, battery status, and cell temperature, which then go into the system of torque limitation. And then this is mixed and you get your target torque at the end. And you see, even now, it's clear for everybody what is happening or what do we want to achieve. So the requirements are already in here, and it's clear, documented for everybody, so you have an overview and it's easy understandable. We have our system, we have our functions, the controller inside the functions and the outside, which, with the environment, with units we don't have in real parts. So, like I said before, the real part there was only the driver and brake pedal, and then you get to the bigger picture, where you have more inputs, and you can see, this is running on our control unit, and there we have our environment unit with the IOs to the actuators and the IOs to the sensors, which is then everything outside is simulated, and you have the one control unit. But you can extend this like you want, so you can start with just driver torque and then add, for example, even your battery management and so on. And this is the big advantage, and you can use it for the next guys which are coming after you. And yeah, that's the advantage. We have functional and logic interfaces with our calculations, where you have a traceable signal view. You can directly see from where to where is our signal going. This is also important for you that you use styling guidelines, so the signal goes from left to right, so that it's really easy to read. You have signals and parameters. Normally you use dictionaries, which is possible in MATLAB, that you can use the data dictionaries and define the data objects, so which dimension they have, what data type is it, and your description. So this is then also documented and easy understandable for everybody. And yeah, if you use the right data types for your variables, then yeah, you could generate a smooth running system and have an interface for your real-time measurement and application. What's also possible, you can use modules and libraries where you put in specific functions. The advantage of this is that you can develop on the functions, or a different team could develop different functions, and you can provide this then later to everybody else and have one complete system where you can work on. This is also possible to use referenced models. When you use referenced models, the advantage is that yeah, you can make own projects of it. You can they can have their own data dictionaries. You can do then their own tests inside the system. And in the build process, the advantage is that you can use parallel build, and then this is faster because it only checks if there were any changes and then builds this new if there were changes. Yeah, some modeling guidelines. So this system you see on the first view, you see nothing because it's just one color. You don't see where are the inputs, where are the outputs, and that's why you should organize it and yeah, make subsystems so that you have a clear overview at the beginning and it's easy understandable. You have your inputs on the left, your outputs on the right, and you have your functions in the middle. And yeah, it's easy documented then and understandable for everybody. What you should also take care of, that you name it in a way that is understandable, because yeah, you see here's coming in speed, you have a calculation, you have a check, and you have post-processing, but you don't know what's happening. So it's not, yeah, it's not. Then it was useless to use model-based design because it's not clear what's in there. Yeah, a way better is you name your inputs, you color them in different colors, you have your constants in specific colors, your inputs on one side colored and your outputs on one side. These color guides, I think there's also a MATLAB function you can use, but yeah, if you start with it, it's clearly understandable what happens where, and yeah, it's not only here's the status and the result, but you can see what's really happening. Yeah, in our example, with the target driver torque, the limitation, the output, and the aviation, and these subsystems, where you can see, for example, do I have any arrows in the system, then you have the torque limitation or your SOC status, with then your torque limitation for your reconfiguration, or you have your cell temperature with your limitations on torque, depending on it. So if you build up your system, for example, like this, it's easy understandable and it's clear and easy to use. What is also possible in this, what we also need is the validation and the verification. The goals are the detection of faults, the quality of your system should be better, and you should prevent errors and create trust in your complete system. And if you start early enough with testing your software and your hill system, or even parts of your system, then you can start testing even before the car is built, or you can use it. So complete testing is it's not possible. You can't think of every fault. That's there are always faults that come you don't think of and before. Your testing depends on the environment, and these are the basic principles, I would say. Typical methods for testing is the model in the loop testing, so the interaction between your controller functions, like I described before, and your test model and plant. So what's your complete environment. Then you could use the software in the loop testing, where you have the generated production of code of single model functions, or you test the functions for themselves before you provide it for the others. You have processor in the loop testing, and you can use hardware in the loop testing, and this should be done. One more time, the overview of our system, which we are showing above. We have the two Arduinos, which I described before, with the torque, brake, analog inputs and outputs. So we have one environment Arduino, and one Arduino for the ECU functions. You can also use your specific ECU, but from the Arduinos, the advantage is that you can use MATLAB and use the MATLAB models and generate code for them directly. Yes, this was, then we had, you can do your testing points, what do you want to test? So when braking, there should be a negative torque of recuperation. This you can test so that you have the 120 Newton meter, which is then also limited so that you don't overshoot this. Also you can generate test for torque reduction, for the cell temperature between 86 and 75 degrees, for example, and thresholds for cutoff for higher temperatures, even no recuperation, and torque cutoffs for battery systems. And the good thing is that you can set up automatic tests for all these points, and if you change anything on your functions, you can then go through these automatic tests and you can get a complete report where you see what is working or what is not working anymore. And this is for the example of the torque path. There we had the test scenario for the throttle pedal and the brake pedal, and in the upper view. In the second one we have the torque, so the target torque from the driver demanded. There we have the SOC where you can see, and on the bottom is the temperature of the packs. So we were at the beginning we were at SOC, for example, here at 100%, and we tested. Then we released the throttle pedal and pressed the brake pedal, and because of the SOC was too high, there was no recuperation. Then that, or it was, no, in this case it was limited, and the yellow one would be the target, what the driver would want, but it was limited to 0. At a later stage you see that when you're braking again, that the recuperation is working and you have a rise of SOC, and even then the temperature is also rising up, and you can see that the recuperation torque is limited in a curve. And you can automate these tests, and then you have your functions controlled, and you can do these checks. And of course, you do this not alone, so you can use different departments, and teamwork makes the dream work. Use your workflows, your checklists, use automatizations, like I told. The sum of best parts is not the best system. Yeah, that's also true. Try to be the best, except that you're not. That's what sometimes happens to the best. We've seen it here. Also that good teams have problems, and but you can take care of your systems, and I wish you a lot of luck for the rest of the event, and have fun on the event. And perhaps if you're more interested and want to see in detail or a small example and want to know more, you can come up to our pop-up stand. We're there until, I don't know, 6 o'clock or something like this. So if you have time, please come by. And that's from my side. Are there any questions? Yes.
I'm not totally clear about show the function of view and technical view.
Yes.
It's missed the technical view completely. Why? How is it connected to what we just saw?
What do you mean?
How is the technical view connected to the functional view, which you elaborated on?
In the technical view, you can see your inputs and your outputs, and I don't know what exactly you mean.
There was just a slide, 23
Yeah. This one.
Exactly. Yeah.
Yeah.
We didn't hear about the technical architecture anymore, right? So.
Yeah, it depends. There are two options what you can use. You can use functional architecture, or you can build up a technical architecture. That's
Okay, that's a choice.
That's a choice, yeah. Of course, it's a choice. Also, yeah, but yeah, here you have the overview of what functions you have, and this is then clearer what in this function, how is it done then. So what functions do I need, and what do I have in this function that it works, or in the system that it works at the end.
So in fact, if I would go deeper into the functional architecture, as you showed me a couple of slides later, I would have a corresponding technical view as well?
Not exactly, yes.
Sorry about that.
No, it's no problem. Yeah, so in your, you see technical things in here in your input system. So you then also have your analog throttle pedal, brake pedal, and so on. There are all the inputs, but if you go into the driver torque system, I can go into it and then you will see. Yeah, for example, where is it? This one, yeah. Yeah, you have your, how is it done then? There you have your technical overview, your technical architecture in the deeper model. So, in this functional overview, the signals are going into a bus system and go down, and you have a flow of signals which are going through the systems. But in the systems, you have your, of course, your technical side.
Let's skip in functional description because it's so too deep already. You can directly describe it, I think, anyway. Got that? Okay, makes sense?
Yeah, but you could do it, but then the possibility is that you lose lack of clarity. So if you only use your technical, you don't use subsystems, then you have something like this. Yeah, then you have a system looking like this. Even if you color it, you won't get into a clear.
Okay, so this triggers the next question. When to switch from a functional view to a technical view?
Yeah, so I would recommend that you, you start. For example, we started. You have a physical side or electric side. If you think of the environment model, for example, then I would divide and go always deeper. So you have a physical side, electrical side, and I would make a subsystem of them both. Then I would go into, for example, the physical side, and I would describe my modules, for example, or my functions, what I need. Let's say functions for environment, functions for cockpit, functions for the engine, functions for the car itself. Then you would go deeper in it, and for example in the cockpit you would then have your overview of steering wheel, your other boards where you have your buttons and rotaries, for example. And if you then go again deeper, then you would have your technical side. So I would try to, it depends on how complex it is. I would not use a subsystem for two blocks, which are inside them, but I would also try, so if this would be only one part of a bigger picture and not only for the torque path description, this would be again a subsystem of a.
Okay, thanks.
So this would be. So this is just going deeper inside, that you don't lose the overview and that you. Yeah. That's what I would recommend.
Good enough, thanks. Yeah.
Yeah.
It's clear.
So this is just yeah. This isn't also you could say yeah, in the next bigger picture this so where would I locate this? This is on I would say torque path, something like this, and you have your let's say your battery management could be on a complete different side. Any more questions? No one? Then, thank you.